Okay, in the previous lesson, we have talked about the body plots for the second order system and the first order system, or the any transfer function that you provided to the to the MATLAB. Okay, and so by hand we can calculate the results of this function based on the or the as a function of the frequency characteristics. Just remember that in the root log section we talked about the stability, right? And so in the root logs techniques we follow the rules of the roots or the pole locations. But in the frequency domain we have another rule to define to stability or the controller design, which is called to the Nyquist Criteria, right? This is the Q. Okay, so what this tell us, this Nyquist criteria, is directly relating to the stability of the system. But which one of them has a closed loop system? To the open loop frequency response. And pole location. So what's the meaning of this sentence? We talked about the stability, about using the Nyquist criteria for the closed loop system, but based on the just looking or examining the open loop frequency response, just like the root locus techniques. Okay, and so stability can be checked, but it can be extended to the transient or steady state properties of the response. Okay, so which means that we can design the controller based on these informations. Okay, and so the Nyquist criteria or the frequency domain design are focused on to to design your controller with the basis of the frequency response. For example, if you have the unit step signal, you don't need to analyze this Nyquist criteria because we can design our system based on the root locus. But if you have the input just like the sinus or the cosinus, and then you need to check out to to these frequency responses based on the Nyquist criteria. Okay, so these are the basis for our relations. Okay, and so consider the following closed loop system. Consider the system like we have the RS reference signal in here, just like this one, and so we have the GS, the open loop transfer function, and so we can apply the unity feedback, or in this case we can extend to our results to the HS. This is the sensor frequency representations. Okay, and so we must talk about the or weakening condition of the four terms in here, just like this one. First of all, the relation between 1 plus GS times HS and GS HS. This is important because we can examine our frequency response based on the stability criteria, but between the relation of the closed loop and the open loop poles. For example, if we want to evaluate the open loop frequency response, and then we can decide that this stable or not, okay? But the closed loop system must obey this rule based on the what? The open loop one, okay? And so these poles should be evaluated in here. And in the second relation, the relation between to the what? To the zeros of 1 plus GS HS and this one term, this is one term, and the poles of TS. This is the closed loop transfer function poles, okay? And in the third case, we need to talk about the concept of mapping, okay? Points. And also, in the fourth place, we need to talk about the mapping contours, okay? These are the four regions should be discussed in this lesson, okay? First of all, in the first place, we need to talk about the relation between the 1 plus GH and GH, okay? And so, letting to the what? Letting the GS is equals to the NG, numerator G, and denominator G, and HS can be considered as the NH and GH, DH, okay? And then we can say that the G times H is equals to the what? The NG times NH divided by DG times DH, okay? And also, what's the other condition? Other condition is the closed loop characteristic equation. It's given in here, just like this one. This is the what? The 1 plus GH is equals to the what? The 1 plus NG NH divided by DG DH, and so we can yield that the DG DH, right? DG DH plus NG NH divided by DG DH, okay? In the first place, just look at in this system the poles of these terms is equals to the what? Is equals to the poles of GH1, right? And so this characteristic equation poles and the GH poles is equal, same, right? It's the same. And so this is the first relation, but the second relation is that TS is equals to the what? The G divided by 1 plus GH, which is equals to the what? The NG DH divided by DG times DH plus NG times NH, okay? And so the second relation coming from these terms, okay? And so the closed loop transfer function is equals to the what? Is equals to the this characteristic equation, zeros, right? This is the same. There are two concepts in here. And so first of all, the relation between the GH and 1 plus GH at equals to the poles, right? But the closed loop transfer function poles are is equals to the what? The 1 plus GH zeros. This is important property to create what? To create the Nyquist criteria, okay? And then, but this is so simple. Just look at, okay? And we need to map, convert to S-plane into the FS, just like the root locus. Just remember that if we want to locate the antipole or assign the antipole at S-plane, we should add the what? Some vectors to this plane. And so we can define what are the new mapping rotations in here, just like this one. And so this is always given in the what? A complex number. For example, for s plus 5, substituting s 4 plus j dot 3, and so these are the new location on this map, and so s plus 5 is equals to the what? 9 plus 3j. Okay, this is the mapping. Okay, and so in the root locus we always use the what? This mapping, because if we locate any poles in here just like this one, and so we can locate everything in here. And so how we can use this property in here? Mapping contours are to what? For example, if we are using the fs mapping function in here, s minus 0 1, s minus 0 2, blah blah blah, and s minus pole 1, s minus pole 2, blah blah blah. And so in the s plane, for example, we have this contour just like this one, for example q. This is the s plane. Okay. And if we apply the fs in here, and so this could be removed or the transferred to the what? Another place in here, just like this one, q hat. Okay, this is the f plane. This is the complex plane, but this is different because we have the some poles or the locations to carry this signal into the one place. Okay, and so assume that in a deeply understand manner we have the what? The fs 1 plus gs times hs. See that? These are the closed loop transfer function, right? This is the poles of the closed loop transfer function. This is the characteristic equation, and then we can transform the R basis as to the what? To the R closed loop transfer function, just like in the root locus, and then we can define the new plane, new mapping methods in here, just like this one, and then we can draw to the what? To the another place in here, just like this one in the s plane, sigma and j omega. And so we can define the some q points in here, just like this one, and so we can use or build the contour in here, and so we can build the what? The zeros and poles, right? And so each of them should be directed with the what? With this notation, just like in the root locus, guys. Okay, this is the v1, this is the v2, v3, and v2, and this is the v3, this is the v4, and this is the v5. Okay, and so if I apply to what? The fs is equals to 1 g times s h, and then we can convert this system into the what? Into the another contours in here, just like this one. Okay, this is the radius of this term, just like in the body plot in here, but this is the what? The 1 plus gh plane in here. And so what's the values of the r? Just like in the root locus, v1, v2, this is the zeros, right? And so v3, v4, v5 is the poles, right? And so we can transform the any s plane into the what? Into the characteristic equation plane. We just use this s plane to characterize its stability, but if we have this information, this characteristic equation, we can build the characteristic equation plane in here, just like this one. Okay, and then we can check the stability of your system, because this represents to the what? To the r stability in here. And so we can write the formula. We can formulate to the what? To this one, n is equals to the p minus z. The n counterclockwise rotation of center b. This is the b. Okay, this is the a, and so p is equals to what? The number of poles of 1 plus H inside contour A. Okay, and so if we have the any contour in here just like this one, we should calculate the number of the poles of these terms, and also this is the number of the zeros. 1 plus GH inside contour A. Okay, and so the number of zeros, number of poles, and the counterclockwise rotation of the center of these terms is coming from what these relations, right? This is the open loop poles, open loop poles, just like this one, and so these zeros must be calculated this one. So if we have the any pole in here, if we have the zeros in here, and so just remember in the root locus, we have add to what? 2 degrees zeros plus degrees, right? And so poles minus degrees, right? And so the concept is simple. 180 degrees must be satisfied for these conditions in the root locus, but in the frequency analysis we can just use these zeros and these poles and this open loop poles and the closed loop poles must be equals to each other. And so if we have the total rotation of these terms in the frequency domain, not just the angle one, if we calculate this formulation, and then we can talk about the stability of your system. This is the Nyquist criteria, guys. In the root locus, just remember that we should focus on the whole degrees must be equals to the 180, and the GH must be equals to the -1, right? And so, but in the frequency domain, we just utilize the zeros and the poles, and these zeros and poles subtract each other, removes each other in order to provide the stability criteria. This is the simplest example or the simplest explanation about the Nyquist criteria. Okay, because in this case this is also the poles of GH, right? The 1 plus GH and GH has the same poles in here, and so we can conclude that therefore if we check the GH poles checked then we can reach the system stability, because it's also the closed loop poles of these systems with our difference in here, with our difference that we have 1 plus GH instead of GH, so we should add to -1 for rotations. What is the meaning of this? These concepts is the simple. Just remember that in the root locus we have these conditions, right? This is the characteristic equation, right? In the root locus. But if we have the frequency response, and then this GH must be equal to the -1, right? And so if we are looking for the frequency response, not just the unit ramp or the parabola signal, and then we need to add the -1 for rotations in here, just like this one. And so in conclusion of that, the -1 is in here. If we have any frequency response, and so we can search the whole area in here, just like this one. But if a circle is completed to cover this -1, and so our system is unstable, because this pulse is going to cover the -1 values, right? Because these contours possess every values of this fs plane, right? And so just remember, if we have this equation in here in the root locus, and then we can search the whole area of the characteristic equation, and we can assign the poles at the system. But in the Nyquist criteria, we have the frequency response. We always covers or rotate or counterclockwise or the clockwise rotation can be happened in here because it's frequency. But in the root locus, we don't have such kind of informations. And so this -1 should be given in here. This is the what? This is the Nyquist criteria. And so we can conclude that what is the Nyquist criteria? If a contour A that encircles, which covers to the what? To the entire right plane or right half plane is mapped through GS HS. This is the open pole, but the closed pole is also equal to this one. And then the number of closed poles Z in the right half plane equals the number of open loop poles, which means that this is the equals of this one. Okay, and so that R in the right half plane minus the number of counterclockwise revolutions and around -1 of mapping that is the same with what the zeros Z P minus N, which are known as Nyquist diagram. This is the general definition in the control literature of the what the Nyquist criteria. But the idea is the what is the same with the what with the previous explanation of R representation. This is the condition of these terms, and so we can check the what the rotations around to what the -1 because it's frequency. Okay, and so how can we determine the what are stability in these examples? First of all, we can create an example in here. Assume that we have block diagram just like this one. The R plus minus 100 divided by S plus 10, 1 divided by S plus 3, 5 divided by S plus 1. Okay, and so C is given in here, and this is the unity feedback. And so what's the question? Determine the stability. Okay, so solution is simple. GS is equals to the what? The 500 S plus 1, S plus 3, and S plus 10. Okay, and we need to replace this value with what the S is equal to J omega. Okay, because also we need to search the frequency response, not just the real one. Okay, and so we get to what the JW is equals to the what is equals to the 500 JW plus 1, JW plus 3, and JW plus 10. Okay, and also we can get that the 500 of the watt minus 14 omega square plus 30 plus J 43W minus W over 3. Okay, and so in the complex conjugate form we get to the watt to these coefficients 500. Okay, and also minus 14 W square plus 30 minus J 43W minus W over 3. Okay, and so in the complex conjugate form 14W square 30 square plus 43W minus W over 3 square. Just remember, this is the what? This is the complex conjugate form. Okay, and so we replace S with the what with the JW in here. Okay, and so now we can analyze the R system in here, just like this one. We have now the frequency response characteristics, just like in the Bode plot in here, and so we can write that. These two formula should be copied from in here. Okay, this is the first of all. This must be copied in here, just like this one. Okay, and so also we need to copy of these things in here because we should check these values in here. Okay, and so in order to draw your plane, we must first to the what draw the S-plane in here. And so this S-plane, for example, at the B, we can drive the contours in here just like this one. Okay, W is equals 0, and then we can select the minus 10, minus 3, and minus 1. These are the open loop poles, right? And so we can draw the water lines in here just like this one. But in the frequency concepts, we can say that if our system is stable, and so if we have this contour in here just like this one, and so minus 10, minus 3, and minus 1 should be given in here at the last place. Okay, for example, this is the Q. But how we can calculate this formation in here? Because based on the different frequency responses, we need to check to what the frequency is equals to the what is equals to 0, and we need to also to check to what the frequency is infinity. We can decide what our system is stable or not based on what taking the test of the different frequencies in here. And so our calculation is simple. S W is 0, and then JW must be equals to what? The 500, and we have 1, 3, 10, and so the 30, and so 50 divided by 3. This is the R plane, and also we can give the what the W is infinity values, and so this JW is equals to the what the J times 500 divided by omega over 3, right? This is the case of the what the R concepts in here. Okay, this is equals to the what these terms. And so the other important thing is that we have 3 poles, which means that 3 times minus 90 degree is equals to what? Minus 270 degrees phase degree is happen in here, just like in the root locus techniques. Okay, and Third of all, for the watt, for real part is 0 with to the watt minus 14w square plus 30 is equals to the 0 because it's a real part of the system, and so omega must be equals to what? The 30 divided by 14. And if the imaginary part of this system is 0 and with the watt 43w minus w over 3 must be equals to the 0, and w is equals to what? The 43 for the imaginary part, and the real part is equals to the 0. And so these are the case of the what? The w is 0 and w is the watt is 500 w over 3. Okay, so how we can create this Nyquist plot in here? So if we have these conditions in here, just like this one, just remember that these values for the watt, for the real and the imaginary part, we can say that if we take the whole the values in here at 4 j times 30 divided by 14, this is the real part, and so 500 times 0 minus j 43 30 divided by 14 minus 30 divided by 14 over 3, right? And so this is the another real part in here, and also 43 30 divided by 14 minus 30 divided by 14 over 3 and square, it's equals to what? A minus 836. Okay. This is the watt, the real is equal 0. And so also we can calculate the watt j 43 in here with the same idea. 500 times watt minus 14 times 43 square plus 30 minus 0, because the imaginary part is 0, right? And so minus 14 times square root 43 square plus 30 square and 0 j. Okay, and so this also equals to what? 0 minus 0 743. Okay, these are the case, but for the what? The imaginary is equals to 0. Okay, and so we need to draw to what? To Nyquist plot in here. First of all, we need to put the what? Minus 1 in here. Okay, and so this is the real part, this is the imaginary part. Okay. So first of all, just remember that as the v is equal 0, 50 divided by 3, right? And so is the v w or the frequency is 0, and then we can put the what? The 50 divided by 3 in here. Okay, at the imaginary parts is equals to the 0 in here, just like this one. What? But we have the frequency response in here, and so we have the limits in here, just like this one, minus 0 70 48 7 8 7 4, right? And so also the if the real part is 0, which means that we have the what? The imaginary axis in here on the imaginary axis, and then we can write that this part is equals to what? The minus 836. Okay, these are the case for the what? For the limits, and also 36. Okay, so we have this kind of rotation in here, just like this one. See, and also we have the circle in here with the radius of the what? The 500s v1 v2 v3. This coming from the what? The open loop pulse 1 2 3. Okay, so also we can have the one circlement in here, just like this one. okay? Because we have the frequency values in here, just like this one, and so the R limits in the watt in the real part and in this part. And just remember that we have the watt, the W is infinite value, J times 500 divided by W3, right? And so this W3 can be represented in this form. But this is the important part. We don't have any encirclement about the -1, which means that no encirclement around -1, the system is stable. These are the conclusion about what the frequency response of the R Nyquist criteria. Okay, but we don't need to worry about the R conclusions in here because we have the MATLAB for the what, for two solution of these terms in here. Okay, and so how can we create the R MATLAB Nyquist plots in here? For example, comment and x3 Nyquist. Okay, and so for this system we have the what, the 500 s plus 1, s plus 3 and s plus 4, right? These are the system, and so the zeros is empty and poles is the -1, -3 and -10, right? See, and also the gain is equals to 500. Okay, so we can use these nominations in here with the what, the figure and the Nyquist can be called in here for the what, for the G is equals to the what, Z, P, K, zeros, poles and gain, right? These are transfer function, and so this G can be given in here. And so if I run this code, I'm sorry, grid on must be also given in here. Okay, okay. And so if we have this nomination, and then just see that we can draw these lines in here just like this one. We don't have, just see that, -1 point in here, and so we don't have any encirclement in here, just like this one. And so we can check that the R open up and the close up system are stable in here. Just look at that. This is simple, but maybe we can assign the +10. This unstable system, we know that. And so if this is the unstable system, just see that this is the +1, -1, and so this encirclement drives the what, the R conditions in here, just like this one. And also -10 is coming from, in this case, so we have the what, and these values, just see that this is the 16, 50 divided by 3, right? These are the conditions. And also we can say that this is the what, is the -80, right? Our calculation is that the minus to what? Our calculation is the what, -80.36. But it's okay because at the zeros we have that, right? Just see that in the zeros, just see is the -8.3. okay, and so our algorithm and the calculation is true in here. Okay guys, and so this is the decibel plane in here. Just see that this decibel must always be minus in the stable system, because we cannot increase the input signal at the output one. Okay, and so if we have any positive ratio in here, just like this one, we don't have any stable system. But in this case, we don't have any match in the watt in the -1, and so we can say that our system is stable, right? This is simple. Okay, in the next lesson, we will focus on another properties of the Nyquist criteria. Okay, but if we want to calculate the manually of the Nyquist criteria, and so we can check the Holder poles or the system coefficients in here, just like this one. This is the manual calculation of the simplest way for creating the Nyquist plot. Okay.